So we're at the top of the hour. I think we'll go ahead and just start with the introduction and give Rajesh a little bit of time to get his slides set up. So thank you all for joining us. This is the Concurrent Session C for Gateways 2020 with the theme of managing data research products effectively. We have 3 presentations. Each will be 10 to 12 minutes, followed by Q&A for about 3 minutes. We will have 15 minutes at the end of the hour to do a wrap-up discussion, so I hope you all will stay tuned for that and give maybe some broader questions for our authors to answer. But starting up first, we have GeoEDF, a plug-and-play workflow framework for Earth science research by Rajesh Kalyanam. Rajesh, would you like to start?
Yeah, sure. Thanks, Claire. And I'm sharing my screen. You can see it now, right? Awesome, thanks. All right, well, welcome everyone. I wanted to start this demo of GeoEDF with a quick preview of GeoEDF in action and then maybe move on to some technical details. So here is a really simple illustration of a workflow that's pretty common in hydrology. So it's actually depicting a pre-processing workflow where satellite data that's stored in a NASA DAC or a distributed active archive center, which is their distributed repositories, needs to be processed in the context of a watershed and then use the resulting data for a hydrologic model. So the data in the NASA DAC is actually HDF files, which if you're familiar with geospatial data, it's actually a gridded raster format. The watershed itself is actually a shape file, which is a vector file that contains a bunch of polygons showing the different subbasins. And so the goal here is to essentially take a weighted average of the gridded values in the HDF file for maybe one of the sensor values. In this case, we're looking at the leaf area index, which is related to vegetation cover, and then get a weighted average for each of the subbasins so that you can then use it in your hydrologic model. So if this was a savvy researcher, then you would expect that they might maybe automate some of these pieces. So they would probably write some code that downloads data from this NASA DAC, maybe use some GIS libraries to do the masking and aggregation operation to get the weighted averages and then use that in their model. If the researcher wasn't as savvy or if they were in a hurry, then maybe they might just go to the NASA DAC's webpage, download the data from there, use a desktop GIS tool like QGIS or something, do the weighted average that way, and then use it in their hydrologic model. So what does GeoEDF let you do? So in GeoEDF, you can actually write a workflow that looks something like this. I will get into these individual pieces in a few minutes, but the essential message here is that you can write a really simple, high-level sort of declarative workflow. In YAML syntax, you point it to the endpoint where the data is located. You can use things like wildcards and other options to query for data. You provide your authentication details to this repository as the first step, and then the second step, you point to the shapefile for your watershed that you want to model. Put in a reference to your data that you've downloaded in the first step. So you write this really simple high-level workflow file, and then you use GeoEDF to essentially execute it. So let me just reset my Zoom. So if you go all the way down here, it's essentially just a 3-step process. GeoEDF is at the bare bones just a Python library, so you can import the library, instantiate your workflow. It's going to prompt you for your authentication password because you don't want to store that in plain text in your workflow file. Once that's done, then you can have it execute, and this takes a while. So while this is running, let's talk more about what GeoEDF actually is. So, all right. So as you've seen, a lot of the workflows in the geosciences are usually just data wrangling workflows. So you often have to use data that's maybe collected by satellites or a survey from like USGS or something. So most of these data sets are collected by large organizations and then managed in their own data repositories. And so a majority of your time is usually just spent wrangling data before you can use it in your research. And we want to free researchers from this responsibility and sort of help them maybe focus more on their science than in the data wrangling, which is often the boring parts of your job. And this also has a pretty significant relationship to reproducibility, because as you've seen, if you have a researcher who is doing this on their desktop, then that's pretty hard to translate and share with other people. And so even if you have a science gateway, your researcher might either just be using it when they need to get access to HPC resources, or they might do all of their processing offline, then just put up the final results on your science gateway. And that's not really a very sustainable approach to fair science. So the ideal situation is it's what's depicted on the right, and that's what we hope to achieve. So the goal is that your researcher can come to a science gateway, define a high-level workflow in some powerful but user-friendly language, ask the framework to execute it, and then now that you've got a gateway which has all of these data publication and annotation tools, then you can essentially leverage all of that to publish both the data and your workflow and keep track of provenance. So that's our eventual goal. And so GeoEDF really is designed to sort of help you bridge the gap between this current state of the art that's represented on the left and then what we hope to achieve on the right. So this is a 5-year project that's funded by the NSF CSSI program. We just completed our 2nd year. It's led by a pretty large group of multidisciplinary researchers. Our PI is Carol Song, my boss, who comes from cyber infrastructure. We've got several science PIs who represent different earth science domains who provide most of the initial use cases for this project. So GeoEDF really has 3 key design principles, and this is what we use to sort of operate and sort of achieve the goals that I laid out in the beginning. So our first goal is to take a complex geospatial workflow and then try and break it down into its constituent data access and processing steps. So once you've identified these steps, then our next goal is to then build these abstract but reusable building blocks that can help achieve these individual pieces, so individual data access or processing operations. And so once you've got those reusable building blocks, then essentially connect them to cyber infrastructure frameworks that you already have, so that you can then help promote fair science principles by letting your workflow run completely in a CI or a science gateway environment. So GeoEDF has 3 main components. There's data connectors, which implement these access operations, data processors, which implement the processing operations, and then a workflow composer that allows you to connect connectors and processors together into reproducible and reusable workflows that can run in a variety of computer environments. But operationally, these are just Python classes. So connectors and processors are just Python classes that implement a standard class interface. The workflow composer has 2 pieces that you just saw. So there's the syntax itself that tells you how you can compose these connectors and processors together into a workflow, and we use YAML for that. And there is a workflow engine that's essentially a Python library that's built on top of Pegasus, which is a workflow management system that allows you to essentially define this YAML workflow, and then the engine takes the YAML workflow and then figures out how to execute the corresponding connectors and processors in whichever computer environment we've set up for that. So let's, with that sort of quick overview of GeoEDF, let's go back to our workflow. You can see it's running here, but then if you sort of apply the design principles that I just talked about for this workflow, then you can see the first step essentially was where you wanted to get maybe HDF data from a NASA DAC, and then use that and then process that along with a shapefile. And so there's really two pieces to this workflow. So you have a connector that's doing the task of essentially getting the data from the NASA DAC, and then you have a processor that's really generic. So all it does is it takes an HDF file, it takes a shapefile that has polygons in it, and it calculates weighted averages for each of the polygons. So it's not really a domain-specific processor. It's a more generic, reusable processor that can be applied across different domains. So then if you go back to look at the workflow itself, that's really just a collection of instances of these Python classes that I talked about before. So NASA input, which is our connector, is a Python class. These are the class attributes, and all you're doing here is just representing an instance of that. So you're providing the URL and your authentication details. The HDF EOS shapefile mask is a processor. Again, that's a Python class which has 3 class attributes. One is the HDF file that you want to process. The second is a shapefile. And then finally, there is the list of data sets from the HDF file that you want to use. You can have any number of data sets here. So why and how would you create a new connector or processor. So our goal here really is to sort of solve all of these pain points for our researchers. And so we will build these initial set of connectors and processors based on the use cases that I mentioned before. But there's also the notion that we don't want this to be a project where we are building a huge repository of things that people may not really need. And so this is really intended to be a sort of community-driven project. So once we have a few examples of connectors and processors, then we hope that our researchers would then use that template to build their own. And since they are Python classes, they are pretty straightforward. So let's, I have some trouble moving this thing here. So let's talk about this workflow a bit more. So, so the end of this workflow, you essentially get a new shapefile here that has a new field which has the weighted averages filled in. But then if you're working in Python, then that's not really something that you can visualize very easily if you're familiar with the different Python libraries. And so we may want to convert it into a format that's maybe a bit more useful. So you can, for example, write a processor that takes a shapefile, converts it into GeoJSON. And this, again, is a really simple Python package. All you need to do when you're writing a connector or processor is ensure that you've used the right package structure and implemented the right methods. In this case, for a processor, you need to implement a process method. And then that's all you need to do. And I should mention that connectors and processors are actually encapsulated and packaged as singularity containers here. And the reason we do that is because that makes it easier for you to execute it across different environments without having to worry about the software dependencies. And so we have a helpful script here that allows you to build an image. And then once you have those singularity images, then now you can use this to write a new workflow, which has 3 steps. So after you're done with the first 2 steps, you can tag on your shapefile to GeoJSON processor at the end as a 3rd step that takes the input from the 2nd step and then creates a GeoJSON. In the interest of time, I won't run that workflow. The other one's running and it's taking a while. So you can do the same thing here. And then once that's done, I'm just going to skip right to the end, assume that that workflow is done and I have it run before. But then now, since I have a GeoJSON, I can visualize it pretty easily with a Python mapping library like Folium. And so there you go. That's essentially the final output. So skipping really quickly back to my slides. So yeah, so as you might have gathered, I was using a Jupyter notebook there to demonstrate all of this. And really my intent there was to show that this is intended to be a package that can be installed across a variety of CI environments. So it doesn't have to be a specific science gateway or a particular framework. But then the production setup would look something like this. And this is something that we're still working on. So on the top here, you have your contribution process for connectors and processors. We use GitHub for that, just regular open source pull requests and feature branches. And we have a CI/CD pipeline that essentially just builds the singularity containers when you, as soon as you create an update for your particular connector or processor or add a new one. And we have a singularity registry that hosts all of them. The piece here at the bottom is something that we're still working on. We are actually working on integrating GeoEDF with Hub 0-based Science Gateway, my GeoHub, which is our production gateway. So that's still work in progress, and we hope to have it done soon. So we are shooting for December to have that done on my GeoHub. But the one that I was demoing today, that's actually just a Docker container that you can download from this link here, and you can run it on your local laptop and build Singularity containers right there in that particular Jupyter environment, and then write your own workflows. And we've actually got our colleague Jack Smith, who's been using that to develop his own connectors and processors. So with that, I will stop there and put up the slide with all the links and contact information. Thanks.
Thank you very much, Rajesh. We have our first question from Chun Han. So this is, how can you manage large data case to load the data?
Okay, so so the workflow itself, the way it's designed, our main use case is that you're pulling in data from large remote repositories. So there's nothing really that's coming down to your Science Gateway or your CI. So when the workflow runs, it's running on a remote resource. It might be running on a cluster. And if your first step is a connector that's pulling down the data, then that pulls it down to the cluster and then it works there. So the only thing that's transferred back is the final results. And so there's no intermediate data that's transferred back. None of the data that's pulled in any of the steps is transferred back to your gateway. So, so as long as the connector can pull in data from the remote repository, use it in the cluster, then it'll work. We do intend to support several protocols. So right now we do things like HTTP and FTP. We are planning to do OpenDAP, but then if you maybe had a large data set and you wanted to use Globus, then we can write a connector that uses Globus to pull in that data into wherever the compute is.
Perfect. Well, thank you very much. And I think there is one more question in chat, but maybe you can answer that, or we can talk about it at the end of the session. But really appreciate your time today.
Sure.
So next up, we have Andrew McGill with GeoWeaver as a gateway to manage distributed geoscientific workflows.
Hi, thank you, Claire. So I'm Andrew McGill. I'm a developer at the Texas Advanced Computing Center and at SGCI. Today, I want to present to you GeoWeaver, which is a project that I worked on through an EDS engagement with SGCI and Dr. Jensen Sun at George Mason University. So I'm going to talk about what GeoWeaver is, how it works, what makes it special, our future plans, and hopefully take some questions here. So what is GeoWeaver? GeoWeaver is a web platform that enables you to manage deep learning workflows with provenance across distributed resources. We've geared it towards earth scientists, although I think it could be useful for many people. We hope that it helps earth scientists manage these large amounts of data that they have to process over often many different systems. So how does it work? Let me go back to this slide just for a second. As you can see here, we have different types of things here. We have hosts and processes and workflows. So let's talk about how those work together. So we can register different types of hosts. Here we're going to register just a regular server that we're going to connect to through SSH. We can use this to store files or run execution processes. Here we're putting in the IP address and some authentication information. And we'll see now how we can take a look at this. We can, right now, we can just view files on this system, which we'll do here. This is a video, obviously, and this is not live. There's our file listing. Okay. We can also add Jupyter servers as hosts to participate in our workflows. So here we're going to add Jupyter Notebook host, calling it Jupyter VM. We give it the URL and port. And we're going to connect to it really quickly. Don't have any notebooks yet, but here you see that we've connected to it. And we actually proxy the WebSocket traffic through GeoWeaver, and I'll show you a little bit later why that's kind of neat. So we have different types of processes that we can run on our host. Here, we're going to add a bash script. This script is just going to download some imagery to process later in our workflow. Give it a name here. We have this little editor here where we could type it in or modify it. We're actually going to run it on that VM that we added earlier. I won't run the whole thing, but you can see it get started. Just put in our passwords again. Like Rajesh said, we don't want to store that. And so we can see the log in real time here in our console. We go over to the process, say, look at the history, see that it's running. We can actually stop it if we want here, which we won't. We'll just let it continue to run. Go back to our console and see how that progresses a little bit. And see there, it's connected and starting to download the archive. Okay. And we can upload or import Jupyter notebooks. Here I'm going to upload one notebook. I'll just say a word about this notebook. I have an undergraduate degree in geography, but I don't do a whole lot of it. Dr. Sun works in the Geoscience Center at GMU. So that's kind of his focus. I went to this tutorial at University of Colorado to find these really neat notebooks that kind of teach you data science with geospatial processing, and I recommend them to anyone who's, I'm sure all you are very familiar with it. Anyone who wants to give a tutorial to somebody to learn more. It's really neat. And then we can take a look at the history of that process that we ran earlier to download the imagery. We can get a full listing of the output, full log history here. And GeoWeaver records everything that we do. So it's going to know all the processes we run. It's going to know all the output, when we run it, what the results were, if there were any. We can download results. And then we can go to our VM and take a look at the imagery that was downloaded and unarchived here in the imagery folder. And we can even download from our remote server if we want. I think we do here. And then it's important, I want to show you that we can link these processes together in workflow so that we can have independent processes working in parallel independently on different resources, and then we can link them together sequentially here so that one process is triggered when another one finishes. And here we'll just save this workflow. So I imagine a lot of this is very similar to what all of us are doing to kind of make our lives easier, but I wanted to talk about something that I think might make GeoWeaver unique, that feature of proxying the WebSocket traffic through the server allows us to store versions of our notebooks as we work on them. So here I'm just going to make a very simple change. I'm going to change the path to that imagery, and I'm going to save it. And GeoWeaver listens for that save command. Now, it could listen for other things. It could listen just for us to execute a cell. At the moment, we're just listening to the save, and it makes a separate version of that Jupyter notebook that we can go back and look at. We can download. It helps us to retain provenance of our workflows. This is a new feature that we're really proud of. Here we're going to look at the history. And we can see two versions. We can view our previous version, which was the one I uploaded. And then let's take a look at the new version. Here we have some changes to the file path there, the imagery folder. And then if we want, we can download the original version. Okay. So future work, this is very much in development. Dr. Sun just was awarded a grant from NASA to continue development on this. I think that a major goal for our next feature is incorporating support for Google Earth Engine, which is something that we're currently working on. There are a lot more things to come also, and I'd be interested in hearing your feedback. So acknowledgements here. This project has been supported and funded by ESIP-Fed, SGCI, and NASA very recently. And the following people have contributed: Dr. Sun, myself, Li-Ping Di, Annie Burgess, and Jason Tullis. So I'd like to, here's our contact information. I'd like to take any questions that you might have.
Perfect. Thank you very much, Andrew. And I think our first question actually was the tutorials that you mentioned earlier in your presentation from Rebecca.
Okay. Sorry, let me look at the chat. I'm kind of lost. Where's the chat? Okay, chat. Oh, yes. What was the name of the tutorials? Let me go back to that. slide I have written down, but it's probably easiest if I go back to the slide here. It was, yes, this one here. Okay. I think I can just probably follow this link. The tutorial is, it's kind of an online textbook, intermediate Earth data science textbook. Let's just follow it. So it's all right here, and they have just tons of tutorials of doing really all kinds of things. Look at the chapters here. So if you go to earthdatascience.org, you can find it. Also, my slides are right here at my name, andrewmcgill.github.io, and I will upload a PDF version of this so you can hopefully follow the links. But let me go back to this right here, earthdatascience.org. Really nice.
Excellent. And thank you for sharing that resource. Rajesh has also a question for you.
Okay.
Do you use an existing workflow engine to manage data staging and workflow planning?
No, we're not actually. It's all done through SSH, and we're using libraries for that, but we don't kind of have like a framework that we're using right now. This is all Java on the back end and Spring Web Framework, JavaScript on the front end. It's pretty low on libraries and frameworks, but I'd be interested if you have some that you've looked at. Do you have any thoughts on that?
And Rajesh, you're welcome to unmute if you'd like to follow up that question.
Yeah, that was going to be a lot easier than typing in. Yeah, we looked at several workflow frameworks. We looked at Airflow, Luigi,
Oh, right.
a couple of the more popular Apache-based ones. But then we settled on Pegasus just because it does a whole lot of the data staging behind the scenes for you pretty seamlessly, so you don't have to really worry about where your data is going and how it gets staged to your compute servers. And it also brings the data back for you. And of course, it also supports like containers and all kinds of different environments. And so that was really the best of all worlds for us.
Very nice. Thank you.
Great. Yeah, and we have one more question. Looks like, yes, one from Junhan. So do you use a cloud platform for the back end? And I think there was also maybe another specific thought there about the hosting.
Right. So this is hosted on the web. It's still early days in development, so I think it's probably most useful installing locally if you want to use it at this point. And there are some features that are finished, but we're still working on it. But it is deployed just like a traditional web application. It's not. It doesn't kind of use any kind of cloud features for deployment and hosting. However, we do want to incorporate support for compute in the cloud, right? So that's where Google Earth Engine comes in. I think that's really big. I'm not sure if that answers the question. I can look at
Yep,
chat too.
looks like it
Okay.
did. Great.
Okay.
Maybe we have time for one more question if someone has a thought they want to ask.
Yeah, I'm just going to unmute and ask, sorry.
Yeah,
So
no.
Andrew, so you mentioned Google Earth Engine. So I thought Earth Engine requires you to use Colab or one of those Jupyter frameworks to get access to their data sets, right? So I thought you won't be, let me rephrase that. I thought you can't use Google Earth Engine to just get the data from this. Are you thinking of getting the data from Earth Engine or using the compute? Because I thought if you had to use the compute, you'd have to use their own platform to do that, and you couldn't use your own Jupyter notebooks.
Well, that's a good question. I don't know the answer for it. I haven't worked on that feature yet. Dr. Sun, I believe, is here, and I think he's been working on it. I'm not sure if that's something that he wants to speak to at the moment. Yeah, unfortunately, I haven't touched it yet, so it's not a feature that I've worked on. But that is a good question. I don't know if.
Yeah, that might just be because that was like a year or two when we were looking at the different satellite data resources that they had. posted on there, and it seemed like you had to actually use their UI and their sort of IDE to get at those resources. So yeah, but that might have changed now.
I will get back to you on that.
Sure.
Thank you. Thanks.
Great, fantastic. Let's head on to our final presentation for today. We will be hearing from Jared McLean, and I should also start by saying thank you very much, Andrew. A great presentation, really appreciate it.
Thank you much.
So Jared McLean will be talking to us about Hawaii's rainfall analysis and mapping application and the decision support tool that they've created.
So yeah, I'm Jared McLean, and I'll be presenting on the Hawaii rainfall analysis and mapping application. So basically, there's a set of rainfall stations around Hawaii that collect rainfall data. We have a set of data running from 1920 to present. So what we're doing is basically taking the rainfall station data and rasterizing it out into a mapping for the entire state, so a continuous map for the state of Hawaii. If you kind of look, so this application provides a visualization and analysis platform for viewing this rainfall data. So if you kind of look at the so you can see that there's a 250 mirror by 250 mirror resolution raster at the base level, and this is what is generated. These are the maps that are generated from all of the rainfall station data. These points on the map are the individual rainfall stations that are provided. So yeah, then if you select one of these, you can see kind of the individual values for that specific station and some of the information about that station. So this main screen kind of allows you can adjust between the map and this viewing area, and can also filter the stations out. So this first portion allows you to create a main focus data set, so to know what data range you want. And currently we only have monthly rainfall data from 1990 present and partial and partially filled. So what the different fill types are there's actually 3 fill types. Completely filled, which is a serially complete data set using multiple techniques to actually try and fill in different values. So fill in all of the values for all of the rainfall stations for every date. But it's a little bit, and it has kind of increased uncertainty because it uses multiple techniques over some of the other techniques. So the main part of this would be the partial filled one, which uses a single gap filling technique to fill in some of the rainfall stations, but only the ones that can be reasonably estimated based on the other surrounding stations. So the reason for this is that some of the stations don't have data for all the different points in time. So that's what that is. And then there's also going to be an completely unfilled, which is just the raw rainfall station values. So yeah, right now this application has the monthly rainfall from 1990 present and then only partial filled. So the partial filled rainfall data for the stations is actually what is used to generate the rainfall map rasters. So if we go to, let me move this. So if we go to this data view panel, this allows us to view the information for individual rainfall stations. So see here, this shows the 7 rainfall stations that are available. This shows a breakdown of the specific station that's currently selected in the viewer. It shows all the metadata for the station. And then currently, not all of the stations for all of the different date periods, we don't have all the daily rainfall station data. So basically what this will do is it'll show all the daily data. We have more of it for a bit further back. Let me go to 2014. There's a lot of, we have most of the data for there. So just pulling in the rainfall station data and rainfall raster data right now, so it's loading. should take a few seconds. There we go. Okay, so this is for February in 2014, and if I select now site, we should have more of the daily rainfall station data. So let this load. So right now what this is doing is it's taking all, so this is just the current monthly data point for this specific station. Right now it's pulling in all of the data for the date range selected. So from 2019 for the specific rainfall stations. It looks like this one doesn't actually have the data load in right now. Let me try a different one. There we go. Okay, so this one has, so you can see this is all the daily rainfall data for the selected station. This is just for the focus month, so for February in 2014. There's a graph down here that shows that, and we can also change this to show for the current year and also for the entire date range selected. So that would be December 1990 to December 2019. Yeah, so this shows a breakdown of all the rainfall station values for that range. So then there's also a basic map control section, which has just in general layer opacity, so you can kind of view the underlying map through it. And then also it comes when the application has two different color schemes for the rainfall raster layer. So monochromatic, which is meant to provide kind of a consistent view of the data. It's just a blue single color scale. And then there's also kind of this rainbow color scheme, which is provide for user comfort. There are some issues with this color scheme in that because it goes from red to purple with yellow in between, it can provide some perceptual artifacts because the yellow areas are actually brighter. They have a greater relative luminosity compared to the other colors. So it kind of draws your eye to those areas, even though there's those are kind of the mid-range areas. And there are actually some color schemes that have been developed that that use the rainbow color scheme, but also provide a more consistent color scaling, which I'm also looking into incorporating into this application. So that should provide a good balance between user comfort and more consistent perceptual scaling. And then there's also this within data exporting. Currently, we're still waiting on the final data set, so this isn't all hooked up yet, but basically what this will be is we'll be able to, users will be able to export the the generated GeoTIFFs for all the rainfall data and also all the rainfall station data. So they'll be able to select between the different counties. So this has different spatial extents if they want just Maui or instead of this for the entire state, they could do that. And then this is just which type of data they want, whether it's the raster data or rainfall station data. And then just for the focus date or the entire date range. So then you couldn't take the data and set just for February 2014 or for this entire date range. So the application also uses, I mentioned the filtering system. So if we go back to the data view, there's also a filtering system for the different rainfall stations. So this allows us to just say to filter on the specific metadata properties of the different rainfall stations. So if you're only or interested in specific rainfall stations, what you can do is say, let's say the SKN, which is kind of the identifying tag for the different stations. You can go through and search for the ones that you want. So yeah, let's say this was a rainfall station that I was interested in. And you can create a filter for that, and then it'll filter out only the rainfall stations that you're interested in here. And then this top part also provides a kind of walkthrough mechanism. So you can go, it has a cache ahead system. So whenever you move through the data set, it starts to load the rainfall rasters and station values ahead of where you're moving. So no, for the most part, if you're using this system, it should be fairly smooth unless you start to go really fast and you often wait a bit for it to load, of course. But yeah, so this specific part's still loading a bit, so yeah. But for the most part, then it's fairly responsive, and you can kind of walk through and see the change over time of the different rainfall levels for the state. Yeah, so those are kind of the main features. Where, and of course, this is still work in progress. We're getting some additional rainfall station values, and we're also planning on putting the ability to filter by custom spatial coordinates. So like you could potentially input a shapefile or something for area that you're interested in, and then only get the values for that area. And also the ability to place custom rainfall stations, so kind of virtual rainfall stations, where you would click on a specific area on the map, and you would be able to, instead of just these predefined stations, you would be able to get like the rainfall data for that specific point that you selected in the map, the rasterized rainfall data, so not just the station data. And yeah, so those are things that will be developed in kind of in the future. So, yeah, so I'll take in questions now.
Thank you very much, Jared. So we have several questions coming in. First one is from Rajesh. This focusing on the raster affected by all of the number of data point stations in that region. So I guess maybe if you want to.
Yes, so affected by. Yes, so the red. So the red area, so this is actually, so red is actually a very low area. So that's one of the issues with the rainbow color scale. Let me switch back to the monochromatic one. Yeah, so this is a little bit easier to tell. So the white areas would be low rainfall, and the darker blue areas would be higher rainfall. So like I said, there are some color schemes that have been developed that use kind of that use a rainbow color scheme. So then that's commonly used in climatological data and with climatological data, which is why I included it. But there are some colors and scales that have been developed that provide a more consistent scaling than where it's easier to identify, which areas are low, medium, high without having the really poor differences in relative luminosity. So.
Yeah, and so we have another one from Chun Han asking, is the climate data freely public?
Yeah, so the point of this is that this website will be available in the public, and one will be able to come and retrieve any of the rainfall station and rainfall raster data. That's, yeah, the purpose is to make it available to as many people as possible. So.
Great. And I guess I had a question of my own. So I guess, do you have any projects that are local to the University of Hawaii that are going to be utilizing this tool, or is there any use cases of why it's being developed?
So currently oh yeah, actually, we're working with, so there's actually a group of researchers at the university that are working on ranch data. So they're trying to find, so for ranches, for ranchers that handle cattle and stuff, they're using the rainfall data to trying to predict basically how to spread out cattle, and I don't recall exactly everything that they're doing, although basically using climatological data to try to improve the quality of ranches for Hawaii. And this rainfall data is one of the data sets that they're using.
Very interesting. So it's almost as a way for them to diversify the pastures that they're sending cattle to, so it doesn't impact the vegetation too much.
Yeah.
So
Yeah, and one of the issues with Hawaii too is that because the rainfall and biomes and stuff change so dramatically over relatively small areas of land, it's a little bit difficult to know necessarily where to place specific herds of cattle and different times of the year. So that's, yeah.
Gotcha. Yeah, and I just wanted to also update and say this to everyone, what was going on in chat. Rajesh and Sean were talking about the fact that the front end is Angular and the back end is Tapas. And front end is also hosted through GitHub pages. So
yeah.
I think that is a great note. Any other questions for Jared before we launch into a general discussion? All right, I'm not seeing any pop through. So thank you, Jared, for a great presentation. It's really exciting to see what you guys are working on. I know that this period of time has been utilized by different groups to kind of treat it almost like a panel. So you guys get lobbied a few more questions that might be a little bit bigger picture, but I think it's a great turning point to come back. One of the first questions I have that I would like you all to think about is, what is the biggest hurdle when building and supporting your tools for geosciences? Rajesh, can I pick on you to be the first one out of the gate?
Sure. Yeah, I think the translation is probably the biggest challenge. I mean, I don't know if that's common to all scientific domains, but I think maybe some domains have a head start, so it's a lot easier for them to sort of, I guess, visualize the different computational aspects as well. But then if you're in the geosciences, then it's just like, for example, let me take the example of GeoEDF. So I mean, there's some amount of work that they would have to do to actually write these connectors or processors, and so there's always that challenge in, I guess, them making the transition from just using a desktop tool that seems really easy, that they can just use whenever they want it, and it's a lot lower barrier to it, even for students. But then having them transition from there to using a science gateway, I think, is the biggest issue. And there's a lot of commercial tools like ArcGIS that make a lot of things really easy, and so you're always sort of competing with those. So I think that's probably the biggest challenge in, I guess, in building CIs for geospatial research, at least, because there's a lot of things that you can just do with commercial tools that's just not in the scope of science gateways. So that's my initial answer, at least.
Thank you. Jared, Andrew, do you have any thoughts to that question?
So I've been working with portals for a little while now, but I think I'm fairly new to focusing on geosciences. So so for me, I think the biggest thing in my mind are just the specific technical challenges that we've been working on the past almost year. But if I were to broaden that a little bit, I think that maybe it's a little bit difficult to combine visual interfaces with like highly parallelizable workflows. And particularly if the users don't want to become computer science experts. So, I mean, I think that's just a science gateways kind of thing, right? But yeah, I think Rajesh had a good point that a lot of people are just really accustomed to doing things on a desktop. Maybe it's MATLAB, maybe it's ArcMap, and then kind of creating a system that will encourage them to move to a web gateway. I think it's just that's just that's a challenge, I think. Wonder what Jared has to say.
Yeah, and one of the great advantages of having gateways making data sets easier to access by public. So some of the tools that are available otherwise, it's difficult for someone that isn't necessarily a computer scientist to gain access to it and know how to analyze and work with the data. So one of the nice things about these tools is the ability to kind of take that and make it more easily accessible to them.
Thank you. So I have another question. I would encourage also everyone attending to, if you have a question for our authors, please feel free to put it in the chat. But what is one takeaway that would be helpful for others following in your footsteps?
Well, I can go first again. So I think at least in our case, just building the community, and yeah, it might be this is sort of maybe contradictory to what I was saying before, but then I think building the community and sort of building on the features that you had before, or I guess establishing the community first and then building on the features that you had before is probably the best thing we've done so far, because this is really the third iteration of geospatial tools that we've been building. And then it started off with a couple of researchers first, and we had GABS, which was the previous iteration of GEOEDF, which added data management and tools in HubZero for geospatial data. So that sort of was our bait and switch, if you will, to get them onto HubZero. And then once they were locked into HubZero and they started sharing their data with other people, then that sort of adds value. And so once you've demonstrated the value of and this is sort of adding on to what Jared was saying, once you've demonstrated the value of them being able to share data and collaborate with the other researchers, which is not possible with the desktop tool, then you can build on that. And then they can, and GeoEDF really was something that they also mentioned to us that that's a pain point with being able to wrangle data. And so I think once you've established maybe a small foothold there in the community and then had them realize the value of a gateway, then you can build on that and then start adding new functionality that I think goes a long way in building the community and sustaining it as well.
Yeah, I'll go ahead and go next. I think that's something that maybe I've learned. It's taken me a while, but I think I've learned that perhaps it's a good idea not to try to take on too much, to find some specific contribution that you can focus on instead of trying to make a big perfect system. Make some iterative improvements by doing something that maybe hasn't been implemented before, and then coming here and sharing it. I think that instead of like in the next year, me trying to come up with a perfect system, I think it's better to just focus on something really specific and then kind of share it with you guys and learn from what you've done. That's actually taken me a little while to learn. So that's my 2 cents. Jared?
So kind of fun to build on that point of taking specific things and trying to kind of improve on it. And yeah, it's trying to find what's currently available and create changes to it to just improve upon it so that it's easier for accessibility. A lot of my work is accessibility of data, so making it easier for people to get the data and be able to analyze it and work with it to improve research.
Excellent. And I don't see any new questions in the chat, but I'll throw one more question then at you all. So as developers or folks that are working with development teams, what resources could people look into or that you find very helpful for your work that you can find online today?
Well, I've been at this for a while, so I don't know what would help someone coming new to this, but I think we've helped wrap up a couple of students over the years, and we've had summer interns. And I think the biggest issue, well, more than tools, I guess maybe I'll answer it in two ways. So the biggest issue is just all the background knowledge that they have to like sort of learn before they can even get their hands wet and get started on things. So I think that's probably a challenge that we haven't really figured out how to solve yet. Just because if you're working in like geosciences, then there's just so much domain knowledge that you have to know, and then technology just keeps changing. And so if you have maybe undergrads, then they don't really have exposure to things like containers or just CI platforms in general, unless it's someone who's really well versed in that. So I think, yeah, and since I think containers really may be the most revolutionary thing that I can think of that really help in development, because I mean, you're not really stuck to a platform. You can play around with it. You're not going to mess anything up. You have complete control. So you're not really sort of waiting for someone else to help you install maybe a package or something, so you can admin your own environment. So and I think that's what I've seen, at least. So anyone who's been familiar with containers usually has a lot easier time just getting up to speed, I think. And I don't know if that's just general system admin knowledge that sort of helps you with other development tasks. Yeah, I think that sort of really helps wrap up development. So that's probably what I would say is a really useful tool.
So I think I have just a very super general answer to that. And I don't know if Jensen agrees with me, but I really like using Python, and not just for the science bit, but also for the whole project. We had to do a lot of debugging to get the WebSockets to work, and Python's just really easily accessible. You're right into the code, and so we were debugging in Jupyter Notebook source and in Tornado, which runs the WebSocket portion of Jupyter Notebooks. And it's just really nice to be able to just walk through it, see what's going on with the handshakes and so forth. So that's my recommendation, Python. I should mention also, we are also using containerization with Geoweaver, and that can be very helpful as well. Jared?
Yeah, I think it kind of depends on what specifically you're doing. I mean, for my portion of things, I use Angular a lot. Angular has a really good tutorial that was developed by Google, who actually maintains the Angular framework. And I think there's a lot of stuff like that. Any major frameworks now will have good walkthroughs of how everything works, and just going through and getting a feel for how it works, going through their documentation, going through and tutorials that are available. Now trying to identify what technology you're planning on using, and just kind of search for resources for that.
Fantastic. Well, thank you all for your time today, and a great round of presentations. I think we all are virtually applauding for you, even though you might not hear it. But thank you. And I think at this point, we will go ahead and do our last bit of announcement before wrapping up. So after the break, which is a 30-minute segment, we will have Learning Labs, and this is a segment that is unique to Gateways 2020, Gateways in general, as a conference series, and it's a mixture of hackathons, short conversations, and even some demos or impromptu sessions. So Learning Labs will begin at the marked session rooms, which you can find in Kiko Chat. Topics are posted at the welcome help desk on Sched and also listed in the rooms displayed on the left-hand side of Kiko Chat. So thank you all for your time and questions and answers, and we'll talk to you all in 30 minutes.
Thanks, Claire.
Thanks.
Thanks very much, Claire. Thanks, everyone.
Bye, everyone.
Bye.